Probably this other guy doesn't need an introduction, but he's a professor of physics at University of Wisconsin-Madison. He also has appointments in statistics and computer science in Wisconsin. In addition, he's the director of the University of Wisconsin-Madison Data Science Institute. His background is in particle physics. He, for example, played a key role in the discovery of the Higgs boson at CERN back in 2012. And since then, he has been active in this space of like data science and machine learning and physical sciences, broadly speaking. Especially relevant for our workshop today is that he has made some of the foundational contributions to simulation-based inference. He's one of the leaders in this area of simulation-based inference. So we are very happy to hear about his thoughts on navigating the design space of simulation-based inference. So,
okay, great. Thank you, Mikhail. So it's a pleasure to be here. Also, I'm just like super happy that Stamps exists. I mean, Guy and I were walking in this morning and just talking about how this the topic squarely intersects with our own interests, and there are a few things. Oftentimes, it's like from the physics or statistics community or something. So it's super nice to have like actual professional statisticians, joining it, and that we're all talking together. So that's fantastic. So this title, I was thinking about, I was wanting to talk about some kind of some new things, which I hope to get to at the end, but also, just realize that there are all these different versions of simulation-based inference in terms of the types of problems that you have, the things you see in astronomy and neuroscience and particle physics all have like some different kind of shape. I would say the problem has a different shape, and so the people that are working on it tend to like flesh out techniques that are appropriate for those approaches, and it can get a little bit confusing if you're primarily coming from one of those communities. So I wanted to give kind of a little bit of an overview. Mikhail and asked me to give somewhat of an intro. So the first part is going to be an intro, and at the end I'll try to add a little bit of new things, and apologies if you've seen some of these slides before. So what I usually start off with is just this kind of statement, which I think we can all agree with, which is that science is full of very high fidelity simulations. And the way I think of it these days, when we think of a scientific theory, less and less is it like an equation on a blackboard, and more it's like a bunch of those and a lot of software and code that puts it all together. And oftentimes you have kind of hierarchical multi-scale models that describe different kinds of phenomena, and you plug them all together in order to achieve these very like high fidelity state-of-the-art simulations. And like in the lingo of computer science, you might say that simulators are generative models because they generate synthetic data, but they're not kind of a black box generative model that doesn't have anything inside of it that really means anything. They're causal models that have some kind of mechanism coded inside of them. And that's really important because it allows you to extrapolate to unseen situations and consider the effect of different types of interventions and things like that. You can use it for experimental design and principle. And of course, this goes along with all of the investments that you see in terms of scientific computing, all of the improvements and the infrastructure around scientific computing. So we really want to harness these simulators to do the best science that we can. And then the kind of ironic piece is that these simulators, as great as they are like very awkward and difficult to work with when you want to do certain kinds of tasks like statistical inference or certain kinds of experimental design or decision making. Oftentimes the thing that you would want to do, the simulator just doesn't give that to you kind of directly, and I'll get be more specific in a second. There's this quote, which I won't spend too long, which maybe you've seen from Paul Dirac, which kind of hints at this sort of ironic situation that oftentimes the underlying laws that you're kind of, or like the mechanism that you're thinking about, that's not the thing you're arguing about. You kind of agree that that's a reasonable description of the system, but when you go to simulate everything, it becomes just kind of too complicated and kind of intractable in some way. And so this was already kind of pointed out in the context of quantum mechanics by Paul Dirac, a long time ago. So the statistical framing I'll use in terms of some notation. On the left, I'm thinking the parameters of my statistical model, I'm calling them theta. I'm imagining the kinds of data, whether it be observed or simulated data, I'm calling x. That forward direction, or the kind of predictive direction, is, sometimes people say forward modeling or generation or simulation or prediction, whatever word you want to use. And there's some kind of statistical model that's describing what would the distribution of the data look like if you specified the parameters of your model. well. Inside of those simulators, oftentimes there are other random variables that you don't observe in your actual experiment. So those are the latent variable Z. And so the simulator you can think of as then defining a statistical model that jointly describes the observed data, the latent variables conditioned on, given these parameters of interest data. And then the other thing that we want to do is, given some observed data, we want to infer something about the parameters of interest, and that's this kind of inverse problem, which is difficult. When we talk about simulators, there are sort of two broad classes, and they'll both be relevant, but it's kind of maybe useful to just say it explicitly. Is that, oftentimes when you hear simulators in the physical sciences, people think about fluid mechanics and things like that, and those are certainly our types of simulations, but those are deterministic types of evolution, and you also see that in, for instance, in-body simulations in cosmology and things like that, or like dynamical systems. So there are those kinds of simulators, but then there are other kinds of simulators that are intrinsically stochastic. And so those pop up when you have either like Markov models, or sometimes of the treatments of like molecular dynamics or statistical physics problems like Boltzmann distributions, or things that involve quantum mechanics. There's usually some kind of inherent stochasticity involved. And so the emphasis of my talk is mainly on the second class, but I will come back to the first class a little bit at the end. And this video that was playing was kind of an example of, like a toy example where you're not necessarily keeping track of how the balls are bouncing around through the nails, but what you observe essentially is like, where do they land at the end? But the simulator is sort of describing all of that. And then if you wanted to say, what's the probability that you land in one of these bins, you would kind of need to integrate over all of the possible paths that you could take to land in that bin. And so that integral over all the different latent variable scenarios and configurations that would lead to the same observation often is like intractable. Like that can become very, very complicated. All right, so this motivates basically this class of new kinds of statistical inference methods where evaluating the likelihood, which would be like the typical thing in many approaches to statistical inference, you would kind of just write down the likelihood and then you would do something with it, whether it be Bayesian or frequentist. Here we're just saying that likelihood is intractable, but we can still sample synthetic data from the model. So that's the kind of high-level version of the setting, or one of the settings of simulation-based inference, but the way that at least I started working on it. This setting was often referred to as likelihood-free inference, basically because the likelihood is intractable. And that's fine. I preferred using this term simulation-based inference, partially because it puts a little bit more emphasis on the role of the simulator, and also because in many of there are exceptions, but in many of the cases, the first thing you do is try to approximate the likelihood, and then your approach to inference is basically the same thing you would have normally done. So it's not like you're throwing away all of statistical practice and replacing it with something new. So here I feel this framing puts more emphasis on the fact that, like, what is the problem? The problem is that the likelihood is difficult to estimate because of the simulators. Okay, so I'm going to give a concrete example from particle physics. You don't need to know particle physics for this, don't worry. But oftentimes when we talk about the theory, people talk about the standard model of particle physics. Here it is written down, which in some, in the terms of quantum field theory, that's great and all, but it doesn't like directly tell me what I expect to see at the Large Hadron Collider, right? So what usually happens is you learn how to take those equations and start to make predictions for scattering processes. And so you have some particles that are coming in and some particles that are going out, and you basically want to know what's the probability density of the energy and the momenta of those particles that are flying out. That's what you would like to calculate. And this Feynman diagram is like a graphical representation of the calculation that you do to calculate that probability density. And you can do this on a pencil and paper, sometimes many pieces of paper, but like you can do it. But this is also not directly observable. These things, so these particles end up radiating more and more particles, and there's all sorts of effects, some of which are not so easy to write down. They've basically been measured in other experiments, and even some of these processes, there's like every time you see a particle split, it's like there's another latent variable associated to the momenta of those particles. So you start getting a huge growth in the number of latent variables, and so theta were like kind of the original parameters of interest. This ZP were supposed to be the latent variables associated to the energy and momenta of these particles. Then you have the showering process that gives you a bunch of more latent variables. Then those particles hit our detector. Our detector is like the size of a building, and we model it at the micron level. So you get like literally hundreds of millions of latent variables for describing one collision at the LHC in the simulation here. And then you finally get to the observed data. And there's software for doing these different parts of the process. It does have this kind of Markov property, so you really just take the output of one and stick it as the input of the next and to the next until you get to the observed data. And we call these Monte Carlo generators, and they use Monte Carlo methods, but you can also think of those Monte Carlo methods as approximating this integral. So what we'd like to know is the probability density of the data given the parameters. To calculate that, we would have to integrate over this 100 million dimensional latent space, and that's not feasible. So, and then we would need to do this to do typical inference. So what have the particle physicists done for many decades? We sort of use our intuition about, okay, that we've got this really complicated detector data, but we're going to start to refine it and sort of identify particles and sort of try to tell the story backwards, and then basically come up with some well-motivated summary statistic, which is usually just a single scalar. So every collision, there's one value of this number, and then we histogram that, and you get these kind of histograms, and the black dots are like the observed data. The red histograms are the predictions of what we expect from running our simulator forward a bunch of times, calculating the summary statistics and filling histograms. And then we essentially do hypothesis tests at that level. So essentially these histograms are approximating the likelihood, the probability density of that summary given the parameters, and we have to figure out how to parameterize what those distributions look like as functions of our parameters of interest and nuisance parameters. Okay, so we've been doing that for a long time. This is similar to the kind of Diggle and Graton have a paper about doing simulation-based inference with kernel density estimation, histograms, kernel density estimation, not a huge difference. The problem with this approach is that if you need a really good summary statistic, or you start making it a higher dimensional summary statistic, at which point, trying to do density estimation starts to fall over. And so histograms certainly don't scale. So the other, common approach is approximate Bayesian computation. This was excerpts from a website from 2014. But here you just see these things like a class of computational statistical methods for Bayesian inference under intractable likelihoods. Talk about it's an important tool for this large and diverse segment of the scientific community. Particle physics is not here. It's kind of interesting. These two fields sort of developed totally independently and had very little interaction as far as I know. And so the ABC, probably many of you know, I'll just kind of say quickly, but you have a prior, it's a Bayesian approach, you have a prior for your parameters, you sample from that, then you run your stochastic model to get some data set D prime, that's the synthetic data set, and then you calculate summary statistics for your observed and your synthetic data, and then basically if they're close to each other, then you're going to accept that value of theta. And if they're not close to each other, you're not going to. And there's some sort of ad hoc distance measure rho and some threshold epsilon. And so it's approximate because as epsilon goes to zero, gives you kind of exact Bayesian inference, but there's zero acceptance probability, right? So you need epsilon to be non-zero for the thing to work. This is very similar to, to me, does your sample fall within this rho, this epsilon ball, is basically the same thing as saying, does it fall in your histogram den? I mean, it's very, very similar. Both of them this acceptance probability is essentially estimating the likelihood. But it points out in this paper that, okay, in practice, you're not going to come up with a great summary statistic. You're going to use some heuristic to do that. And there will be some loss associated to it. So both this community and what I showed before, there's this choice of the summary statistic is really important. And what you would like to do is maybe not have to rely on that so much and work more with the high dimensional kind of native data, and hopefully not sacrifice power for no good reason. So this was the kind of drawing I drew before. There's kind of this additional step of calculating a summary statistic oftentimes. And just to this is very heuristic, but just in terms of the mental space that I am often in, I'm thinking that the summary statistic is often a scalar. Maybe it's like 2 or 3 dimensional, vector. The parameters of interest are usually pretty small. Like many of these models, they have very few parameters that you're actually trying to infer, like 3, 1, 2, 3, 4, 5. The data might be fairly high dimension depending on what level you start working with your data. It could either be like 10 or 100 dimensional, maybe it's 1,000 or more if it's an image or something. The latent variables are often huge, like in the millions, and that's kind of like the one that's usually the problem for many of the things. So around 2016 is when generative models and the kind of neural network machine learning really started to take off with things like GANs and stuff like that. In 2017, there was a workshop focusing on what they called implicit models. These are basically models that generate synthetic data where you don't have a tractable likelihood, and they start making this connection to like basically what's going on with approximate Bayesian computation, and there's generative adversarial networks are mentioned here. You see density ratios and 2-sample testing. So these different themes are starting to be connected. I was doing some work around this time. And then in 2019, we wrote a review of kind of the first wave, I would say, of these kind of neural simulation-based inference approaches in this paper in the Proceedings of the National Academy of Science. I think it's still a pretty reasonable starting point if you're not familiar with it. But the thing I just say is that since then, it's like totally exploded, right? Like we put up a web page that sort of scrapes the literature. And this was as of yesterday, there were like 11,000, or sorry, over 1,000, not 11, 1,000 papers that have been kind of tagged by this thing. There's some AI model that automatically categorizes them. It's not perfect, but you get some kind of sense of the spread of different areas that are using it. We saw this picture already. There's starting to be communities. This was that one primarily focused on high energy physics. High energy physics has been lagging a little bit. I'd say like astronomy and astrophysics and cosmology are really like probably where there's the most activity, but it's quite broad. So it's exciting. So I'm going to just talk a little bit about the different approaches in that review paper. And some talks, I will talk about approaches to simulation-based inference that don't really involve the neural networks, where you're somehow trying, you're kind of working directly with the simulator, and there's various approaches, and there's some things that are kind of fancy versions of ABC called probabilistic programming, which are cool, but I'm not going to talk about that. Instead, I'm going to talk about these approaches where you sort of try to learn, use neural networks in some way to learn something about the simulator, and go through those different approaches. In that review, we had these kind of flow diagrams of kind of at a very high level, like how the data and the simulator work together and where you do some learning or not, and when you compare them. And the top row are basically the approaches where you work directly with the simulator. The bottom row are the ones where you use some kind of machine learning technique. Some of those use unsupervised learning. Some of those use supervised learning. Sometimes you need to reach inside the simulator and try to extract some more data. You can sometimes, in addition to samples, you can calculate certain gradients or joint density ratios, and you can get some additional information which can really speed up the learning process. And then sometimes you can have a kind of outer loop where you do some kind of active learning to make this whole thing be more efficient. So this is in the spirit of the title of navigating simulation-based inference. I'm just trying to give you a feel of like, the design space of different options and the different ingredients that go in there. So let me talk now in some detail about, so the first one I'll talk about is when you do some kind of ratio estimation. Or actually, sorry, the first choices I'd say are what is it that you're trying to estimate? So the top are, you can try to learn either a likelihood ratio or some kind of density ratio. And oftentimes that involves using a neural network classifier, and that's kind of under the supervised heading. That sometimes is referred to as neural ratio estimation. And you can basically either try to learn like a likelihood ratio where the numerator is the likelihood that depends on your parameters theta over some kind of fixed reference. Or sometimes you can do like a double ratio where both the numerator and the denominator have theta dependence. These are both kind of useful. Or you can do something that's more Bayesian in spirit where you learn something like a likelihood to ratio evidence, or a likelihood to evidence ratio, which is similar to the posterior to prior ratio. I mean, numerically they're the same, conceptually different. The other thing you can do is not do ratios, but try to learn densities themselves. And if you're going to learn a density, it can either be the density of the data conditioned on some parameters, or you can try to learn the posterior directly and learn the density of the parameters conditioned on the data. So those are kind of like, at a high level, the different approaches. And there's kind of, depending on, well, both like, you know, the statistical practices of your field, like the cosmologists like to be Bayesian, the particle physicists like to be, you know, frequentist, you know, that you might want to make a choice based on that, or it might be based something about the dimensionality of the data. If you have if you're doing density estimation, if you have a really high dimensional data vector, that's a hard density estimation problem. And if you have a low dimensional parameter vector, that's easier. So maybe for numerical reasons, you might want to learn the posterior. But for other reasons, you might want to learn the likelihood, and I'll hit on some of those issues later. Okay, so let me talk about this amortized likelihood ratio, which was one of the first approaches. So the warm up here, and I'm sorry if you you know all of this. I don't know. I'm just giving an intro here. But the simplest kind of machine learning problem that you often are introduced with is this binary classification problem. You've got like cats and dogs, and you want to tell them apart. Here it's red dots and blue dots, and the sample space is kind of like a two-dimensional space. You don't know what the density of the red dots is, and you don't know what the density of the blue dots is. You just have samples. If you did know the density, what you would like to do is come up with a classifier that, given a new dot, you say, like, do I think it's red or blue? If you had access to the densities, what you might want to consider is trying to minimize this loss function. So S is a function that's going to take in the data, and it's going to say try to return 1 if you think it's a blue dot, and return 0 if you think it's a red dot. So you could write down this is called the cross entropy loss. It might not be the most obvious thing if you haven't seen it before. You could also do like a squared loss between 0 and 1 as targets, and the same story would be true. So here I'm writing it out as like an expectation, like you had access to the densities. In this way, it's very well posed mathematically. You can use like the calculus of variations to find the function S that minimizes that loss functional, and it's this function. And this function is one-to-one with the likelihood ratio. There's like through a simple transformation. So this is often called the likelihood ratio trick. Okay, which is basically just saying that what the classifier is trying to solve is basically the same as the likelihood ratio, and it's all very related to like Nyman-Pearson lemma and stuff like that. Now, the other part is that the numerator, this first thing you can approximate with samples. So you don't need to know the densities. If you you approximate this expectation with the Monte Carlo samples, and then the integrand or whatever, you don't need to know the density. So this is something you can minimize via samples, and that's what machine learning is good at. So machine learning is essentially approximating this calculus of variation solution, and once you get an approximate version of S, you can turn it into an approximate version of the likelihood ratio. Now that's for two binary, like two fixed distributions, so there's no inference to be done. So the first idea is, okay, let's just take the same idea and kind of generalize it so that the distributions are parametric classes, right? So I'm going to say, I'm going to have a ratio that doesn't just depend on X, it's going to depend on two parameters, theta naught and theta 1, which are the values of the parameters in the numerator and denominator. So you have two different classes of distributions for the red dots and the blue dots that you can sample from. And so now my neural network is going to take in 3 inputs, the data and 2 different values of the parameters, and it's going to try to approximate that likelihood ratio. Or you could get rid of the dependence in the denominator and just have some fixed reference distribution, but you still want to have some theta dependence in the numerator because that's the likelihood as a function of the parameters, right? And so this thing I call a parametrized classifier. And so then once you do that, you have like your simulator. It's got a bunch of latent variables inside that you don't really care about. The simulator outputs some synthetic observations, X. Your neural network is going to take X and the values of the parameters as input, and you're going to use that loss function that I just showed, minimize it, and once you're done, you're going to have this approximation of the likelihood ratio, which you can then use to do statistical inference. So that's like the high-level schematic of the idea. This likelihood ratio, interestingly, is, we say, amortized. You pay an upfront training cost to train that likelihood ratio, and then once you're done, evaluating the neural network is like, takes no time, and so the inference stage, you basically have a very fast surrogate for the likelihood or likelihood ratio that you do inference with after the fact, which is very different from approximate Bayesian computation, right? Approximate Bayesian computation, you get new data, you have to like start over. right? So there's nothing amortized about normal approximate Bayesian computation. So this is done in a kind of frequentist way, but you could use this likelihood ratio in a Bayesian setting as well, and you could do Bayesian inference. So there's nothing, we're not picking any sides at this stage. Okay, so we did do some work where we really didn't assume asymptotic properties of likelihood ratios or anything like that. We really did the full-blown Nyman construction, and it's always kind of funny because I guess people don't always teach that anymore. So I don't know if you know about inverted hypothesis tests and the Nyman construction, but that's like the classical frequentist way of making confidence intervals that have guaranteed coverage. So we've been kind of doing that, and the one nice thing about it is that your neural network doesn't have to be perfect. If your neural network doesn't learn the likelihood ratio perfectly, but you still trust your simulator, then you can generate a bunch of samples and you can calculate your p-values and you can get good, valid confidence sets, even if your machine learning, is not perfect, which it generally isn't. Here's an example where because it's amortized and it's pretty fast, you can generate a bunch of different data, and for each one of them, you can fit and find the maximum likelihood estimate for theta. So here's a histogram of the maximum likelihood estimate of theta, and you can see that it's unbiased. You can calculate the likelihood ratios, you can profile. Here's a distribution of the profile likelihood ratio test statistic showing that in this case, it did actually, follow Wilks distribution and all these kinds of Wilks theorem and the chi-square distribution. So you can do all of the kind of normal things that you might want to do, but you don't have to rely on asymptotics. This is a little bit in the weeds, but I think it's kind of interesting and maybe relevant for some other things, is that you can also get exact inference with a relaxed set of assumptions about how good the neural network is doing. So if your neural network doesn't learn the likelihood ratio exactly, but it learns some monotonic transformation of that thing, so some one-to-one function with the likelihood ratio, then you can do this trick where you say, okay, well, let me run my simulator, and I'm going to make a histogram of my one-dimensional scalar S, which is a likelihood ratio. It's just a scalar. So I'm going to make a histogram of S, and it turns out that if you look at the ratio of densities you get from doing the densities of these one-dimensional histograms, then the Jacobian from the monotonic transformation, whatever, drops out, and you get back to the high dimensional likelihood ratio that you want. So there is actually a weaker assumption that you need if you stick in this extra kind of calibration procedure at the end, which is kind of interesting, but it also points to kind of the first hint that there can be a lot of gray area between, okay, you do your learning and you have it, but how do you integrate it into the rest of your machinery? So at the Large Hadron Collider, there's a lot of machinery for dealing with histograms and doing statistical inference. So there's a case to be made for using the neural simulation-based inference stuff to calculate S and then just stick it into histograms after the fact and then use our normal machinery. Okay. So also along the lines, just a shout out to Anne and team that have been working a lot on frequentist approaches to simulation-based inference that don't necessarily focus on using likelihood ratio-based test statistics, but other kinds of test statistics, and having a kind of modular framework for being able to do all the different things that you need to do. So I think that's nice, and maybe we'll hear about that later. So yeah, in the interest of time, I'm going to keep on going though. These likelihood ratio approaches, if you wanted to do Bayesian things, here's two ways you could do Bayesian inference with likelihood ratios. Maybe I should actually start on the one on the right. Here you see this kind of double ratio that I showed before, where you have parameter dependence in the numerator and the denominator. This is the kind of acceptance, this is this accept reject correction that you need to do for detailed balance in Metropolis Hastings. That's so the Q is the proposal distribution, and this ratio of P's is the kind of accept reject stuff. That's the thing that you can estimate with what I just showed you. And so you can embed it into a Metropolis Hastings type of approach, or since these are neural networks, you can take their derivatives and you can do it in a kind of Hamiltonian Monte Carlo approach if you want. The other thing you can do is try to do this ratio trick, but instead you notice that if you learn the likelihood ratio between this likelihood and the evidence, where you've kind of marginalized out the parameter dependence according to some prior, via Bayes theorem, this is just Bayes theorem written in an unusual way. way, that's the same as the posterior to evidence ratio. So if you learn this thing, you're basically learning the posterior to evidence ratio, and since you know the prior, then you can just multiply and you get the posterior. So that's another way of doing Bayesian inference that doesn't involve any sampling. There's no sampling in this process at all once you've done the learning. Okay, so in this review, we also talked about the approaches that do where you try to directly learn the likelihood or the posterior using density estimation, and that's a kind of unsupervised learning approach. I already made this point at the beginning that both classical ABC and the kind of traditional template-based stuff that high-energy physicists have done are doing density estimation, so that you run the simulator a lot, you estimate the density, but these are usually done in very low dimensions with like very low dimension summary statistics. But if you want to go to higher dimensions, you can do that if you have a good density estimator, which typically we didn't have. But that's the thing that seems like is changing very rapidly these days with, you see all the like fake images and things like that. We have really, really good density estimators in high dimension. And so what you do is you just generate a bunch of data from your model, but you need to keep track of the parameter values you used when you ran it. And then you form these pairs, theta n, xn, and then those pairs used to train a model, and then you can either, when you train the model, you can either have it be like learn the density of x conditioned on theta, or the other way around. So these were some of the first papers that learned that tried to learn the likelihood directly, and then there were other papers that then tried to learn the posterior. The machine learning trick is exactly the same. It's just a different target. This has been the neural posterior estimation has been one of the ones that's been very like seems to be very popular. I think partially because people like being Bayesian, but it's so there's a lot of papers about neural posterior estimation and different flavors of it. Okay. Now I'm just going to make a quick comment about generative models, kind of from the machine learning side. Is there's a bunch of generative models out there. The first ones that kind of really hit on the machine learning side were generative adversarial networks and variational autoencoders. Both of those generate synthetic data. The issue with them is they don't really solve the problem that you want to solve because they are themselves implicit models. So you can generate synthetic data, like you can learn your simulator and then generate new synthetic data that approximates your simulator, but the likelihood is not tractable. So so it doesn't really help. Normalizing flows were the first kinds of approaches that were expressive, that do a good job, that give you a tractable likelihood or a tractable posterior. And so those have been primarily the ones that have been used for a lot of neural SBI. And then diffusion and flow matching models have become like kind of the new kid on the block in terms of generative modeling, and they are very good. They're very expressive. They work well in high dimensions and with data that's kind of trapped to a manifold and all of these kinds of things. They are so they're expressive. They're slower in sampling. But importantly, if you wanted to calculate the density, it's in principle, there's a formula, but it's incredibly expensive to compute. So like it's almost intractable. So like you could do it, but in practice, it's not really tractable. So I think that there are certain settings in cosmology where diffusion models are being used a lot, but it's often, if you look in the details, it's the way that the thing that the generative model is being used for is often different than, it's like often like actually the prior itself or something like that. It's not trying to solve the fact that the likelihood is intractable. Okay. That's not a criticism, it's just an observation, but it's a subtle one, and it can be hard to spot like what's going on when you listen to some of the cosmology talks and the high energy physics talks or something, and like to figure out which category you're in. Okay. The other thing was this active learning piece. I'm not going to say much about it. The main point is that when if you have a prior that's say very broad, and then once you collect the data, your posterior is very concentrated, then you're going to have to sample the parameter space very densely in order to resolve that well, right? And so that requires a lot of samples, especially in high dimensions. So what you might want to do instead is do a kind of not so great job with a few samples and realize, okay, the posterior is kind of over here somewhere with a very approximate posterior, sample more in that region, do a better job, and like iterate and refine to try to focus in on the very concentrated posterior. So these are often referred to as like sequential fill in the blank, sequential neural likelihood, sequential posterior, et cetera. I think you get the basic idea. There's lots of variations on how to do this efficiently, and it's interesting and it's super practical, but I'm not going to say much more about it. In terms of software, there are specialty software that are being developed for very specific problems. Like in high energy physics, we have a dedicated software package that knows about high energy physics problems for like weak lensing their projects. There's a kind of generalist project called SBI from Jakob Mackie and crew, who came from doing more computational neuroscience. One thing that they did, which I like, this is in that kind of a little bit older paper now, but they set up another package which is just about benchmarking. So you can define a problem and then you can try the different methods and you can try to benchmark them, and there are various different metrics to try to say like how good are you doing and things like that. There were some conclusions in that. Because of the people that started with it were doing computational neuroscience, their problems tended to be you have one big observation and then you want to do inference. And so they had this kind of sort of conclusion that the sequential approaches tend to improve on the other approaches in terms of sample efficiency. And that I think is true when you have like, if you have theta that goes to some latence that goes to some observed value that you observe, and you're trying to kind of approximate it like this with some sort of surrogate, that if you do this active learning, that makes sense. However, in some areas like high energy physics, we have hundreds, thousands, millions of IID observations, right? And so there, in some sense, the sample space of the observations, if you think of it as one observation, is huge, like absolutely huge. And it's much easier to think of it as like a bunch of IID observations. And if you do that, it's much more natural to like model the likelihood and just take the product of all the IID observations and then do your estimates that way. So in these situations, the amortized thing is very important, and you need that likelihood to be good kind of for all the different values of X that you might see. And so for different kinds of problems, like the sequential approaches are not necessarily so helpful for a lot of the high energy physics problems. Okay, so that was 35 minutes. I think I have 10 minutes left. I'm going to switch gears a little bit. I guess if there's a burning question, I could take it. We have 15 minutes at the end to talk, but I want to talk about a little bit of slightly more forward-looking things if I can. Okay. Okay, so one of them that I'm really excited about is, and this is a plug of Mikhail's talk from before, and we're going to have dedicated talks, which I'm looking for. So Andrew and company are going to be talking about spatial statistics later, but it doesn't have to be that you have an intractable likelihood, or what you mean by intractable is kind of on a sliding scale, right? It could be that your likelihood is somehow tractable, or it's tractable up to a normalizing constant, but nevertheless, it's either expensive to calculate or something, and these methods can still be used. And so we're going to hear a lot more about that. I think that's a very exciting area, and so I'm not going to, I'll just point that out. I will also point out that in the context of gravitational wave observations, that's not spatial statistics, but it's kind of in the same category. They have a tractable likelihood. It's just like basically Gaussian noise around a template, but that template is incredibly expensive to calculate because it's like numerical relativity and all of this kind of stuff. And there's a bunch of parameters. So there have been groups that are trying to do one big amortized model that can approximate the posterior that you would get. And that's important because before you could calculate the likelihood as expensive, but then to do the posterior, you would do Markov chain Monte Carlo on a supercomputer, and it would take however many days. But we have these situations where if you see some kind of thing, you want to point a telescope like immediately in the sky and see if you can see like an optical counterpart to some LIGO event. And so you need that to be fast. And so these kinds of pipelines will allow you to take in the data and just like immediately say, this is the posterior on the sky for where I think it would be, and go look there, which is cool. Another thing, sorry, that I should have mentioned earlier, but I'm going to say it now. This is a little bit off, but when you do normal MC, you have to do the posterior in the high dimensional parameter space. You're kind of tied to that, right? And so imagine that this corner plot here are the, I don't know what it is, 9 variables or something, 9 parameters that you're trying to get a joint posterior on. In the simulation-based inference approach, because it's already marginalizing out all these latents and things like that, you can also just marginalize out any of the parameters you don't care care about. So you can just directly learn the posterior you care about, like the marginals that you care about, or like any set of marginals that you care about. So if all you care about is where on the sky you should point your telescope, and you don't care about the masses of your black holes and stuff, you don't have to do inference on all of those parameters. So that can be like very useful in practice. Okay, so one of the things that comes up a lot in these is that, the simulators aren't perfect, right? And so we know that, all models are wrong, but some are useful. So this model misspecification is like a very real problem, and I haven't really said anything about it. And it's not that I don't care. I'd say the majority of our time is, is at least on the experimental physics side, is dealing with this problem. So first, absolutely, if the model misspecified, you're going to have problems for sure. One thing to keep in mind a little bit is that the simulator may not be perfect, but it's including all sorts of effects that you can think of, while the kind of other approaches that people have used in the past maybe are making a lot more approximations. So let's keep that in mind. At the same time, if you're allowing these neural networks to start working with very high dimensional data, you're opening yourselves up to lots more mismodeling things that the machine learning could grab onto. So there is more to worry about. One of the most common ways that, at least in high energy physics, I think also in astronomy and cosmology, that people deal with this is to try to expand the model by making it more flexible and adding some nuisance parameters, some of which are a bit ad hoc. They're not always like first principles, but they kind of distort the model in various ways to try to make it so that some setting of the nuisance parameters describe the actual data, and at which point it's no longer misspecified. So the picture kind of can grow, and there can be many more nuisance parameters. We'll hear possibly, I don't know, and Larry's talk tomorrow about this work being done about robust simulation-based inference, which I think is great, and I'm excited about. Maybe if there's time, I'll say one more thing. But the one part I wanted to say, which is really, I think, both methodological, but to Anne's point earlier, it's really being driven by the use-inspired nature of it, is that at the LHC, we have these kinds of these situations that are not like the way I described SBI so far. Oftentimes, the distribution that we actually want to model is a mixture model, and there are mixture coefficients, and some mixture components, and all of the theta dependence sits on the mixture coefficients. And not only that, we know the theta dependence. It's like some polynomial we can write down. So there's no mystery about the theta dependence. The hard part is that the mixture, each component is some weirdo distribution that I have no idea, and it has an intractable likelihood. So in those situations, I might want to try to learn likelihood densities or likelihood ratios that only depend on X for each of the different components C, and then use some, and then recompose all of this thing according to my known mixture model. Why would I not do that? Why would I try to learn the dependence on theta if I know the dependence on theta? So then you get into this kind of semi-parametric situation. So I'd say traditional statistical models, everything was kind of parametric. You have explicit forms for the whole thing. The full neural simulation-based inference, as I described it before, the density is hard, so you use some kind of neural network, but also the theta dependence and the dependence on nuisance parameters is all inside of some big, huge neural network. But what I just described is something where the kind of X dependence is being described by a neural network. The parametric dependence on the parameters of interest is the dependence on the parameters of interest is parametric. And if I had nuisance parameters, then maybe I would say these densities I also don't know. And so I'm going to do that in some non-parametric way that's conditional on the nuisance parameters. So you can do something like that. The other thing is that in the old school SBI, based on templates, histograms, and stuff that we've done at the LHC, we can have hundreds of nuisance parameters. And so we need to describe those densities as a function of this 100 or several hundred dimensional space, and that's expensive. And we have to learn that from simulations. And we can't scan this 100-dimensional space and generate simulations because it's totally intractable also. So what we often do, which is, you can cringe, but it's what we do, is we often just take each systematic, vary them one at a time, plus and minus 1 sigma, and we say, okay, well, we know everything's going to expect it to be smooth, so we just fit some kind of function to that. But we do that for every bin of all the histograms, and if there's multiple ones, we have to put them together. So we assume they factorize essentially in some way, and so that's clearly not has problems, but that's the common thing that's done. So this is like a parametric model for the nuisance parameters that scales to high numbers of nuisance parameters. So you could do the same thing in a neural density estimation approach, but instead of doing this interpolation for every bin, you do it like point-wise in X. Like, so for every observed value, every observed data point you have in X, you can calculate their densities or density ratios for all the like components and all the nuisance parameter variations, and then you use then you interpolate essentially the likelihood values or likelihood ratios according to some thing. And that will still have the problems of making some simplifications, but at least it scales. And it's making the same assumptions we've been doing. So this is what was actually done in the first papers that were published by Atlas and CMS using actual data with simulation-based inference. These took 6 years to push through the collaborations, and so they have kind of high dimensional observable X. There's actually parametric versions for both, I think, the parameters of interest and the nuisance parameters, so there's this kind of table where you could also have parametric dependence on both nuisance parameters and parameters of interest, and the neural networks are basically just helping you with the high dimensional data. And the other thing that we're thinking about right now is that, especially for the dependence on the parameters of interest is maybe motivated by like quantum mechanics or something like that. The dependence on the nuisance parameters is uglier, and we know that these approximations we're making are too restrictive. So there's an effort now to try to use Gaussian processes to model the kind of high dimensional nuisance parameter space that doesn't assume that things factorize, can still be very sample efficient, and then you can regularize it so that you get something nice and smooth out, and possibly even start to include like uncertainty on the interpolation itself. That's like all in progress, but it's something that I think is interesting and in some sense would be kind of like a state-of-the-art situation in applied SBI. With that, I think I'll end. I had some, well, maybe I'll just tease this one thing. I talked earlier about learned summaries and how sometimes instead of using the neural network directly, you can just use your neural network to output a quantity that you're going to essentially use as a test statistic and then stick it into your like histogram machinery. Well, one thing that we thought about doing is that like in particle physics, we have the standard model, which is like, whatever is going on in the universe is very close to the standard model. So there's some parameter point and we want to do inference in that neighborhood. And so we can take that model and kind of expand it around that point. And then if you do that kind of, a Taylor approximation essentially of the model sits in the exponential family. And then you have like the exact sufficient statistics for that approximate model, which you can then use for being your summary statistics. It's very interpretable. It has lots of nice properties. You can learn it. I'll describe stuff, but you basically run your simulator. You do this process that I just described. You extract the exact sufficient statistics for an approximate model that you histogram, and then you do inference that way. It's quite similar to what is in the same paper that's talking about kind of like a exponential tilt to expand the model parameters, but instead of doing that to add flexibility for nuisance parameters, we're actually doing that for the parameters of interest, and we're doing it by expanding an already known, well-motivated model. So it's like very similar mechanically, but the emphasis is different. So I just wanted to tease that. Sorry if that was too fast and confusing, but kind of interesting. And then I'll end with kind of, I don't know, a word of enthusiasm here. Anne already sort of said it, but I mean, I think this is really an interesting time on what's going on. I mean, I think we are going through a pretty profound shift in terms of the kinds of principled statistics that we can do for the physical sciences. And it's very gratifying. It allows us to really take advantage of our best simulations and everything that we've learned about nature, and not somehow like hold back our modeling capability because the statistics can't catch up, and really allow us to advance both of them at the same time. So thank you very much.